So today we are going to do lecture 10. Let me recall things we have done so far. We talked about the concept of an inverse of a matrix. So we said a matrix has an inverse called M if by multiplying M on the either side produces me the identity matrix. And the concept of inverse was only for square matrices, so that we can have both the left inverse and the right inverse. The way we found inverse was basically solving these three systems at the same time. So we said if I can, let us say, if we are in a 3 by 3 situation, if we can solve these three systems and they all of them are consistent, then we know that the inverse will exist. So our strategy was to deal with this in one shot and basically start with the matrix, so-called augmented matrix with A, and try to row reduce it. If you are able to row reduce it and making sure that the left-hand matrix turns out to be I, so whatever matrix you get on the right-hand side will be your inverse. Okay, this tells us a couple of things. Let's see, what does it exactly tell us? So we want to do something called the fundamental theorem. Of invertible matrices. Now, the reason this is called a fundamental theorem is basically it gives you various equivalent ways to understand when a matrix is invertible. So, suppose we are given an n by n matrix. Over some field F. So usually it will be real numbers or complex numbers in our case. Then all the statements that I'm going to write are equivalent. Now some of the statements I'm going to write will not make any sense today because we haven't seen those concepts. But for the sake of completeness, I'm going to put them in this list anyway. So A is invertible. It is equivalent to saying that the row reduced form of A is actually the identity matrix. Now why this result is true? Remember we said when we are going to deal with inverse of a matrix, then if I start with a matrix A, if I can reduce it to I, whatever I get on the right hand side will be my inverse of the matrix. So that means the row reduced form of A must be I. So this thing we kind of get out of the definition itself. What else we can say? If the row reduced form is I, what can I say about the rank of my matrix A? Well, if the row reduced form is I, that means all the rows and hence all the columns are pivots. So that means it's a full set of pivots, so the rank of my matrix must be n. So if I have n vectors as columns of A or n rows as rows of A, all of them are pivot rows and pivot columns. What else can I say? Let's see. A is invertible, we have the row reduced form, we have the rank taken care of. Let's talk about the linear independence. If the rank of my matrix is n, then all the columns are pivot columns. So this means that the columns of A are linearly independent. In fact, we will see another way to check this fact very soon. Since all the rows are pivot rows, so this also tells me that the rows of my matrix, rows of A, are also linearly independent. So what we are saying is, if any of these criteria can be fulfilled by our matrix, then all the remaining things can be claimed. For example, if I create a matrix whose rows are linearly independent, and suppose I have a square matrix, then I can, just because of this fact is true, we can say that the matrix must be invertible. So these are all equivalent criteria. So in mathematics, we have this acronym, which is not very, how should I say, very catchy, which says the following are equivalent. So that means these are all biconditional statements, or you can say if and only if the statements, one of them is true, then all of them would be true. Okay, let's think about the homogeneous system. Can we say something about the homogeneous system? Ax equal to 0. What can be said about the homogeneous system? Well, let's see. If the columns of A are linearly independent, that means the only linear combination of these columns which can produce me a zero vector is the zero combination. So I can say that homogeneous system has only the zero solution. Okay. Now once the homogeneous system has only the zero solution, that means we can now talk about any system of equations, even a non-homogeneous one. So for example, Ax is equal to B will have a unique solution. Because if there is no homogeneous component, that means there is no free variable, and that means the number of solutions for any consistent system will be unique. Now, hidden in this statement is something that one should see. We'll have a unique solution for all B. So in some sense, I'm claiming two things in one go. I'm saying that Ax is equal to B is not only consistent for every B, but it is also going to have a unique solution. So how do I know that it is consistent for every B? That comes from the fact that the rank of my matrix is n. So all the pivots are in the coefficient matrix. So that means that no pivot will enter the right hand side of my augmented matrix. And that guarantees me that I will have a unique solution for every B. Based on this, I can also make the following claim. Remember, Ax is equal to B is consistent if and only if B can be represented as a linear combination of columns of A. So in that case, now I can come out and say that the span of the columns of A is actually entire Rn. So if I have an invertible matrix, its columns will span the entire space, and which means all such systems are solvable and they will have a unique solution. And all these things can be written as, in another form, that the columns or the rows of A will form a basis of Rn. Now right now we are not familiar with the word basis, and as I mentioned before I started writing this result, that there are some terms which we are not familiar with, but I want to have them under one umbrella so that we have all the things under this one theorem. These things we will cover later on when we understand the term basis. But let me just keep on increasing this list to include some future things also. And then we'll focus on some of the results in a little more detail. Okay. Now, what else can I claim out of what we have already done so far? There is one more thing which I am going to write. Again, it may not make sense at this moment. The determinant of the matrix A. So we may not know what determinant is right now, but determinant of the matrix A would be not 0 if A is invertible. Then there is one more thing, that A can be written as the product of elementary matrices. Okay. So there are three terms out here which we perhaps don't understand the meaning of. The basis, the determinant, and elementary matrices. As I said, we'll pick up one at a time. But let me first focus on some of the things which we are more familiar with. So, let us look at a system of equation Ax is equal to B. Let's start with Ax is equal to 0 first. So let us consider this guy. If I know that A is invertible, which is what we are saying over there, if A has an inverse, then what we can do is, we can come here and multiply both sides by my matrix M. This thing will give me identity, and this will give me the 0 vector. Identity times the x vector is 0. So this tells me that the homogeneous system will have only one solution, namely the 0 solution. In some sense, this is another corroboration of this fact that the homogeneous system has only the 0 solution. Since the homogeneous system has only the 0 solution, that means the columns of A must be linearly independent. And since you only have 0 solution, there is no free variable, hence the rank must be n. So you are getting all these things out of some idea like this. So you can prove it using this way of thinking as well. There's another thing which we can say at this stage. Again, we are trying to solve the system Ax is equal to B. I'm assuming A has an inverse. So again, I will multiply both the sides by M. This becomes identity, so I can say x is m times b. And this is going to be the unique solution. Notice, I did not put any condition on b, so that means this system is solvable for every b as long as I am guaranteed the existence of m, which kind of further tells us that Ax is equal to b will have a unique solution for every b, and this is the unique solution for a given b. So these are the reasons why we want to study invertible matrices, and we shall see that these statements will turn out to be very, very useful as we go along. So keep these statements in mind, they are very important, and we will be using them back and forth, back and forth. Let's try. Let's see if we can try to answer a simple problem based on things we have seen so far. let us just first understand the concept of finding a solution. So here is a problem that I would like to go for. Suppose I know that this guy has solution 100, it has a solution. Say let me call that solution as x1, the vector x1. So if I plug in the vector x1 here, that satisfies this equation. Likewise, suppose I know that the system Ax is equal to 0, 1, 0 has a solution, say x2. And let us say the system Ax is equal to 0, 0, 1 has a solution x3. So I'm assuming that A is a 3 by 3 matrix with this piece of information given to us. So question for us is, what is the solution of Ax is equal to, say, 1e pi? Okay. So what can I say about the solution of Ax is equal to 1e pi? Now, the moment I know that these three systems are consistent and their solutions are this, I know that my matrix is invertible. But wait a sec, I am not even given my matrix A. So what exactly, how will I be able to find what I'm supposed to do? So question is, can I find the solution of this system in terms of the given information to us? So here is a simple way of looking at things. Perhaps it can help us. Okay. What we know so far is, if you look at 1e pi, can I say this is 1 times the vector 1, 0, 0 plus e times the vector 0, 1, 0 plus pi times the vector 0, 0, 1. So 1e pi can be written as a linear combination of the right hand sides that I have over here. Now look at this guy. We are saying Ax is equal to 1, 0, 0 has a solution x1. So can I say that this thing is actually A times x1? Likewise, can I say this is A times x2? And can I say this thing is A times x3? Because I know the x1, x2, x3, the solutions are there. So can I now say that it will be A times x1 plus ex2 plus ex3. So A times that vector, I'm sorry, I made a mistake. This should be by x3. So if I multiply my matrix A with that vector, then I'll get 1e pi. Hence we can say that the solution of our system is the vector x1 ex2 plus pi x3. The idea of this problem is to show you something which is kind of convenient for invertible matrices. Just knowing the solution of three systems, we are claiming that we can know the solution for any system. So in some sense, a little bit of information is helpful for us in capturing information for infinitely many possibilities of the right hand side. And that is something which we'll keep on playing in linear algebra every now and then. That there will be a bunch of vectors which can help you understand the information about the entire space. And that is what makes it very interesting as well as beautiful. Okay. So let's try doing a little more about some of the equivalent statements we have seen. There was a term I had used, elementary matrices. Question is, what exactly is an elementary matrix? And how do I know that it can be written as a product of elementary matrices? Okay. So let's come to the notion of elementary matrices. Well, an elementary matrix is a matrix that we obtain by performing one row operation on an identity matrix. So any matrix that I get by performing one row operation on an identity matrix, we will call that as elementary matrix. So let's take an example in our case of 2 by 2. So suppose I have my matrix, identity matrix 1, 0, 0, 1. And suppose I perform one row operation on it. A row operation could be just like multiplying second row by say 2. So I'll get 1, 0, 0, 2. So this is an elementary matrix. Likewise, if you look at this matrix, I'll start with the matrix first, and then suppose I am given this matrix. I claim that this is an elementary matrix because if you start with your identity matrix, question is, can I perform one row operation to get this? So suppose I take minus 3R1 plus R2, you'll see I'll get that matrix. So that means the matrix that I've got is an elementary matrix. Likewise, if you look at this 0, 1, 1, 0, this is an elementary matrix because if I start with identity matrix and I swap rows 1 and 2, then I will get 0, 1, 1, 0. So that is also an elementary matrix. So elementary matrix can be used to represent one row operation. Now let us see what is the effect of an elementary matrix. What is the effect of using an elementary matrix? Suppose I am given a matrix A, and let us say on the left, I multiply it by this elementary matrix 1, 0, minus 3, 1. What will happen? I'm assuming A is also 2 by 2 matrix. So let's see, let's give it some entries. 1, 0, minus 3, 1, A, B, C, D. Okay. If you look at this, if I perform this matrix multiplication, keep in mind, I am multiplied by my elementary matrix on the left of A. Let's see what happens. 1, 0 times AC gives me A, this gives me B, this gives me minus 3A plus C, and this gives me minus 3B plus D. Okay, you will say, well, so what? Look at the matrix that we have got. If I start with the matrix A, B, C, D, and I ask you, what should I do to get this matrix 3a plus c minus 3b plus d in terms of row operation, probably you would say minus 3 times r1 when added to r2 will give me what? Will give me the matrix on the right hand side. So what is the effect of multiplying by an elementary matrix on the left? It helps you perform exactly one row operation on your matrix. Try it with other matrices also. For example, if you tried multiplying it with this one, the effect would be as if I have multiplied the second row by 2. Or if I multiply by this elementary matrix, the effect will be swapping the rows 1 and 2. And this is where elementary matrices are useful. In some sense, now we can encode all our row operations as just matrix multiplications. So we don't have to really learn anything else. Everything can be, in some sense, obtained in terms of matrix multiplication. So let's note down this finding that we have and see how is this useful for us. Okay, so here is our finding. Okay, so to perform one row operation on matrix A, we just need to multiply A on the left by an appropriate elementary matrix. This is what we will use in order to do what we want to achieve. So let's see what are we after. Remember I said any invertible matrix is actually a product of elementary matrices. I will use this and everything, but before I really use this to our advantage, there are a bunch of things we want to kind of understand about inverses. And then we will revisit this idea of elementary matrix. So these are some properties of inverses. In some sense, I'm kind of digressing. I could have done this beforehand, but I just wanted to do it right there, right here, so that it will make a little more sense when we use them. So there are a couple of obvious properties of the inverses, which you can try to prove on your own. So inverse of an inverse is the actual matrix. If you have a scalar multiplied to your matrix and you want the inverse of it, it would be simply the reciprocal of A, yes, the reciprocal of the scalar K, and multiplied by the inverse of this matrix. Okay. This is the property which we are quite looking forward to. The inverses, if they exist, are unique. That means once you have found a matrix which acts as an inverse, that is the only thing which will act as an inverse. And this is another property which is going to be quite a bit useful for us. Now, before we venture into all these properties, these two are obvious, which you can work out the details yourself. Regarding the uniqueness of the inverse, suppose I have two inverses or two matrices claiming to be inverses, then I have to show you that they are both same. This is a very typical uniqueness proof in math. You assume there are two things and then you show they're the same. So let me try proving the third property. So suppose I have two matrices, M1, M2. Such that AM1, M1A is identity, AM2, M2A is also identity. That means they are both acting as inverses of A. So my job is to show you that M1 must be the same as M2. Okay, so how do we do something like this? Well, let's try. Let me start with M1. I can think of M1 as M1 times I. And M1 times I can think of I as, say, AM2. Remember? AM2 is also I, so I'm just replacing I by AM2. Then using the associativity property of matrix multiplication, I can write this as M1A times M2. But then M1A is identity, so it is identity times M2. So this is M2. So that means M1 is the same as M2. So if there were two matrices which were acting as inverses, they are actually the same matrix. So the inverse is unique. Now regarding this fourth property, if you notice, this property seems very innocent, but there's something hidden in here which you should be careful. What it is saying is, if I give you matrix A and matrix B, then the inverse of that matrix would be B inverse A inverse. So first things first, the order has changed. Then we will see why. Secondly, this result is also kind of assuming that both A and B are invertible. Then only A times B will be invertible. So in other words, this result is telling you that if even one of them was not invertible, then this result may not be true. So keep that in mind. So let me try to deal with it over here. Proving this is not that difficult, because once you know the answer for it, kind of. So you are trying to find whether AB times B inverse A inverse is identity or not. Well, using the matrix multiplication being associative property, this gives you A times I is A inverse, which is A times A inverse, which is I. So I have verified that the matrix which we are claiming to be the inverse works as an inverse from the right hand side, and you can show it from the left hand side too. And once, so similarly we can show that B inverse A inverse times AB will be identical. Proof is exactly identical, so I will not go through it myself. You can sort of do it as a practice. But the things which are important, which we want to make a note of, is as follows. So this result is assuming that both A and B are invertible, then the product will be invertible. So question now is it possible that one of them is not invertible, maybe A or maybe B, and yet the product could be invertible? So this is the more important question we need to ask ourselves. Can A times B be invertible? Without A or B being not invertible. That means even if one of them is not invertible, can the product be invertible? Can it happen that we can have maybe perhaps a different formula for A times B in that situation? Or could we prove that the product can only be invertible if and only if both A and B are invertible? So this is the question we want to answer and ask ourselves. Can the product be invertible without A or B being not invertible? Okay, so let's try and see. So I'll come back to the elementary matrices, don't worry about it. It's just that we have to fix a few things here and there so that it will make more sense. Now, let's try to answer this question. I'll at least try to answer it with one scenario, and perhaps you can try to answer it with another scenario. So, what if B was not invertible? Can the product be invertible? Well, if B is not invertible, then what all can we say about B? There are a whole lot of things we can say. For example, we can say, remember the fundamental theorem of invertible matrices? If one of them does not hold true, then none of them can hold true. So for example, we can say the rank of B will be less than n. We can say the columns of B, the rows of B cannot be independent, so on and so forth. In particular, what can I say about this guy? Bx is equal to 0. What can I say about the homogeneous system? If it is not invertible, then that means the homogeneous system must have a non-trivial solution. Let's call it as x0. That means, apart from the zero solution, it must have something which is a non-zero solution. But then, if you look at this guy, AB times x0, okay, would you agree? This can be thought of as A times bx0, which is A times 0, which is 0. So this implies that if you look at this homogeneous system, it's a non-trivial solution. So this means A times B cannot be invertible. This is one of the simpler ways of getting this result. So if B fails to be invertible, then B has a non-trivial solution for its homogeneous system, and that same solution will work as a non-trivial solution for this system AB x equal to 0. And since it has a non-trivial solution by the fundamental theorem, we can say it is not invertible. So at least we know some answer to it, that if B is not invertible, A times B cannot be invertible, even though A may be. So I would recommend you to try to answer this under the condition, what if A is not invertible? Can you have a similar looking proof when A is not invertible? And see for yourself how things work out. In fact, if you remember matrix multiplication, we had given several interpretations of matrix multiplication in terms of linear combination of columns of A, in terms of linear combination of rows of B. So what this is suggesting is, if rows of B are dependent, then the rows of AB are also dependent and hence not invertible. Now imagine if A was not invertible, then perhaps you can say something about the columns of A, and maybe you can prove something about the columns of AB after that. So think along those lines and see if you can come up with a way to show that the result or show that A times B will still be not invertible when A is not invertible. In fact, those of us who are familiar with function composition might be able to see it in terms of function composition, that if you have both f and g as in bijective functions, then f compose g, if it is defined, will also be a bijective function. So it is kind of analogous to that result. Okay. Well, let me close the gap. Remember about elementary matrices. So let's try. Let's first understand it on an example. Suppose I am given a matrix, say 1, 2, 3, 4. That's a good enough matrix. Suppose I try to reduce it, row reduction. So let me first write down the operations which we are going to perform. So I'll say, oh, minus 3 times row 1, then added to row 2. And I will get 1, 2, 0, minus 2. Okay? Suppose I want to take it all the way up to reduced row echelon form. Then what I'll do is I'll divide the second row by minus 2. Remember, I want a row reduced echelon form, so all my pivot entries must be 1. Now I want the pivot columns to be free of all other non-zero entries, so I will do minus 2 times row 2 added to row 1. So this will give me 1, 0, 0, 1. Okay. So the question is, if I look at this reduction, I started with A, and this is the row reduced echelon form of A, which turns out to be the identity matrix. So by the fundamental theorem of invertible matrices, I know for sure that A is invertible because its row reduced echelon form is identity matrix. But let us try to capture this in a simpler way. Well, I should say simpler way, perhaps in an another way. Let us look at this. We said if you perform one row operation, it can be represented by an elementary matrix. So the elementary matrix corresponding to this row operation would be 1, 0, minus 3, 1. So I took my elementary matrix, identity matrix, performed this row operation on that. Likewise, for this guy, let me call the matrix as F. The elementary matrix corresponding to this guy is 1, 0, 0, minus 1/2. So second row divided by minus 2. And let me call this guy as, say, some G. The elementary matrix corresponding to this would be 1, minus 2, 0, 1. So minus 2 times row 2 added to row 1. Now, recall what did we say? We said in order to perform the row operation, you take your matrix and you multiply on the left by the elementary matrix. So if I multiply my matrix A on the left by E, I will get this new matrix, which if you want, you can temporarily call it as B. Okay, so this is your B. Now, if I want to reach this matrix, I will multiply B on the left by F. So I will get F times B as F times E times A. And I will get my new matrix, let me call it as C. Okay. Then, in order to reach the identity matrix, I will left multiply C by the matrix G. So G times C will be G times F times E times A. And this will give me my identity matrix. Okay, so in a nutshell, what have I done? Can I say that A, when multiplied by E, then F, then G, on the left will give me my identity matrix? So first things first, can I say that this guy is product of these matrices will be the inverse of A? So at least I have been able to write inverse of A as a product of elementary matrix. However, I claim that A itself can be written as a product of elementary matrices. So that question is why? Well, since this is inverse of A, that means it is itself invertible. So can I write A as GFE inverse? Okay. And if I use that property of inverses that I just did, so can I say this will be E inverse, F inverse, and G inverse. So suppose I can do all of this, then can we now say that A is a product of these three matrices? However, there is a little bit of caveat out here. You have to be careful. Remember what we said about that theorem? That theorem is only applicable if I know that each of these individual matrices is itself invertible. Because then only you can talk about E inverse, F inverse, G inverse. Question is, how do I know that these elementary matrices are invertible? So here is the question we are asking ourselves. Are elementary matrices invertible? In fact, if they are, then what are their inverses? So let's come back to this thing that we have done. See, these are some things which are very good, very nicely explained by means of examples, and then you understand the theory behind it quite nicely. Look at this. I did the row operation to start from A and go to B. What if I wanted to come back to A, kind of undoing this row operation? What would I say? So what would be the inverse of such a row operation? Well, this row operation is invertible. It says minus 3 times row 1 added to row 2. If you want to undo it, just undo what you have done to that matrix and it will be all set. So how will you undo that? What would be the opposite of this operation? Well, what you did here was you multiplied minus 3 to R1. So the opposite of that would be you multiplied 3 to R1 and then add to R2. And if you go it this way, it will work. So I claim that if you look at this 1, 0, 3, 1, that would be the inverse of your row operation. And you can check that E times E inverse is actually the identity matrix. Likewise, what would be the inverse of f? If you look at the inverse of f, so here is my E inverse. I should use a different. What would be the inverse of this? Okay, so what did I do? I divided the row 2 by -2. So if you want to undo it, you will multiply the row 2 by -2. So this would be your inverse matrix. What would be the inverse of G? What was the operation G? Or operation being represented by G? We said we'll multiply by -2 row 2 and then add it to row 1. Well, if you want to return to what you started with, all you need to do is you multiply row 2 by 2 instead of -2 and add it to row 1. So this would be your G inverse. Okay? So this way, any operation that is a row operation can be undone by basically reverting exactly what you did. So all the elementary matrices are invertible in that regards. That is why I have no problems in getting what I want from here. So in this particular scenario, in fact, I can also find the inverse by just multiplying these matrices appropriately. 1, 0, 0, -2. And this would be 1, 2, 0, 1. So if I multiply these three matrices, E inverse, F inverse, G inverse, I will get my matrix A. And if I multiply them G, F, E, I'll get the inverse of it. So this is the idea behind saying that every matrix which is invertible can be written as a product of elementary matrices. Now, mind it, this is not a proof, this is basically just a motivation of why this will work. You can easily generalize it to a proof, because all you have to do is think of every elementary operation as a corresponding elementary matrix, and the arguments we presented can be generalized to any size matrix. Okay? So at least out of the 10 or 11 statements that we made, we have shown one of them which we were not familiar with. The two more remaining, which are basis and determinant, which we will encounter a little later. Now, the next thing we are going to do from here, I'll introduce it right now briefly, and then we will continue with it in the next lecture. It is one of the most fundamental things about linear algebra. In fact, this is what basically forms the heart and soul of linear algebra. Okay, so this is the notion of a vector space. You may question at this time, well, haven't we just been talking about vectors all along through all the lectures? So why all of a sudden I'm making such a big deal about heart and soul and all those things? Well, the way we think of vectors, we always think of a vector as something with a magnitude and a direction, or like a column vector or something like this. But we want to generalize the notion of vector. So instead of just thinking in geometrical terms, we would like to have vectors, the notion of vector generalized in a broader sense. So let me give you an example. Suppose I take polynomials. Let me confine myself to polynomials of degree less than or equal to 2. So anything which looks of this form, ax squared plus bx plus c, where a, b, and c are real numbers, so there could be 0 also. And that is why the degree could be less than or equal to 2. If I take two polynomials from this family, let me call them as u and v. ux and vx. If I add them up, can I say the ux, let me give this guy some name, p2. Can I say ux plus vx will still belong to p2? Polynomials of pt less than equal to 2. Remember, the way you add polynomials, you will collect the coefficient of x square, collect the coefficient of x, collect the constant terms, add them, make them look pretty. So can I say that the new polynomial that I will form will still have degree less than or equal to 2? There will be no x cubed term coming anywhere. Can I say if I take any scalar k and multiply it to a polynomial, can I still say the new polynomial I will get will still be P2? Now, look at these things. Aren't they similar to what you find in R3? Remember in R3, you said, oh, vectors which look like this, A, B, C. Now, if I take any two vectors, U and V in R3, if I add them up, we all agree that the sum vector will be still in R3. If I take any vector in R3, scale it by a scalar, the new vector is still in R3. So look at the two different worlds. Aren't they kind of behaving in a similar manner? This is the world we are very familiar with. This is the world we are familiar with, but not in the similar way. But aren't we saying that you take two things in here, the sum is still in the space, you scale the thing, it is still in the same space. Aren't we doing the same thing over there? So we want to associate the notion of a vector not to just things which look like this, but to any objects, even things which may look something like this. So for us, polynomials will be vectors, matrices will be vectors, functions will be vectors. And in that sense, we want to have the notion of vector space and see what all things can we do using this.